Hello. You know, it's hard to talk about algorithms when there's war outside. I have a lot of friends in Ukraine. They all are great people. And I don't understand why we're fighting them, why are we killing them. This war must be stopped. So today we'll talk about network flows. What is a network flow problem? You have a graph. Let's say some directed graph. Something like that. And you have, let's say, some liquid. And this liquid is flowing from one point to another point of this graph. So we have two fixed nodes. One node is source, S. It is the source of the liquid. So the liquid is starting to flow from this point. And it is sink. That's T. So this graph, and there's some liquid flowing from this point to this point in the graph. Now, for each edge of the graph, we know how much liquid can flow in 1 second through this edge. It's called the capacity of the edge. So each edge has some capacity. Well, let's put some numbers here. Let's say 10 here, let's say 5 here, 6 here, let's say 5 here, and for example 8 here. Something like that. So for this edge, for example, we can from this vertex to this vertex can flow 8 units of liquid per second, right? And the problem is very intuitive, so we need to find the maximal amount of liquid which can flow from source to sink. How can we describe the flow of the liquid? We will just say for each node how much liquid is flowing through this edge. So for each edge we will fix some number. This number is amount of liquid flowing through this edge. For example, let's say we have, let's say something. We can have, so here's the maximum number, it's 10. So let's say we have, let's say 10 units of liquid is flowing to here. Now it is split here and here. Let's say 5 is here, 5 is here. Now from this point we have 3 units of liquid. So here they joins. So we have 5 from here, 3 from here. So they join, and now we have 8 units of liquid for this edge. So this is how the network flow looks like. What we want to maximize the amount of liquid flowing from source to sink. How to calculate the amount of liquid? What is the amount of liquid flowing from source to sink in this graph, for example? How to calculate it? It's called F. So F is the value of the flow. So it's the total amount of liquid which is flowing from source to sink. For example, for this graph, we have 13 units of liquid. Yeah. How to calculate it? The easiest way to calculate the amount of liquid is just to calculate the number of total amount of liquid which is flowing from the source. So we have this source node. We have 10 liquids flowing here and 3 units of liquid flowing here. So the total amount of liquid flowing from the source is 13. Or we can look at the sink node. So for this node, we have 5 units from here and 8 units from here. So the total amount is 13. Yeah. It is the same for obvious reasons because no liquid is all the liquid which is flowing from the source will eventually go to the sink. So the amount of liquids going from the source is the same as the amount of liquid going to the sink. Okay. Now, let's describe it more mathematically. So we will say that for each node, for each edge, we have the value C UV. It is capacity of the edge. And these red values are the flows. Yeah, so we have another value f. UV is the flow. And there is a simple constraint, so the flow should be at least 0 and at most capacity. Now, for each node, they have a balance equation, right? So the amount of liquid flowing to the node must be the same as the amount of liquid going out of the node. So for each node, we have sum of all ingoing edges. So let's say sum for all u. So for each node v except S and T, we have sum of all ingoing edges. So it's F U V. So this total amount of liquid going to the edge, to the node, must be the same as the amount of liquid going out of the node. Like this. Now, and yes, and the value of the flow will be just the sum of everything going out of the source node. Yeah. No, actually there can be edges going to the source node, so we need to subtract them. So let's do it carefully. So we need to sum everything going out of the source node minus everything going to the source node. Like this. And the problem is to maximize the F. Like this. So that's the Maxwell flow problem. Yeah? You forgot to say everything is clear every 30 seconds. Okay. I'll just suppose everything is clear by now. Okay. It's a nice model, but it's not very useful actually. So for our algorithms, we will use slightly different model. It is the same, but it will make the algorithms more simple. I will explain why when we move to the algorithms. We'll use slightly different models, so we slide some symmetrical model. So in the symmetrical model, we will. What's the problem here? Huh? Yes, make him go. So why not? So in some graph, there may be some edge like this. Yes, you don't need these edges if you want to maximize the Maxwell flow. Yeah, you can just remove all these edges actually, but why? No. So what's the difficulty here? So the difficulty here is we have multiple sums. So in these equations we have sum here and sum here. So we have the sum for all ingoing edges and sum for all outgoing edges. That's kind of complicated. It will make all the future algorithms more complicated because we need to look on all ingoing edges and look at all outgoing edges at the same time. So we'll just merge these two set of edges in a single set. So how we do it? We will add more edges to our graph. So for each edge, we will add the reversed edge. So for each edge of the graph, we will add one more edge, like this. And we'll say the following. We'll say that the flow on the reversed edge is minus the flow of the forward edge. So we'll say that the flow on this reversed edge is minus flow of the main edge. Now, in our algorithm, will be no difference between real edges and these reversed edges. So we will work with them in the same way, but actually, So this is the edge from your real graph. This is the edge you add when you build your graph. Yeah. Now, Now what about constraints? We will say that the capacity of this reverse edge is 0. And for these edges, we have capacity CVU. We'll say that CUV is 0. Well, now let's talk about this equation. So for this equation, we can just say that FUV is no more than CUV. How we can multi-edge? If you have multi-edges, you can. Okay, let's do it here. If you have multi-edges, you can just add these residual edges for all of them. It's also work. Actually, when we don't have cost, when we have simple flow problem, you can always unite all the multi-edges into one single edge with capacity equal to the sum of all these capacities. But in some weighted flows, when we will talk about minimal cost flow, sometimes we need to have multiple edges. Yeah, and that's not a problem. So just for every edge, you make another reversed edge, and that's all. So all these algorithms do not depend on the graph is simple. So you may have multi edges. It's totally fine. No, it will be not it will be slightly difficult to express it like this. So it's actually you do it like this. So you have multiple edges. You have E1 and you have E2. Yeah? And you have different flow. You have flow over edge E1 and flow over edge E2. Yeah. So here, instead of these indices, you just make you need to attach this flow to the edge. Yeah. If you have multiple edges with the same ends, you need to attach different flows to different edge. But that's usually how do you program it. So usually when you program it, you don't have this adjacency matrix, right? So usually when you program graph algorithms, you have something like list of all edges. So you have kind of object edge, yeah. And if you have object edge, you can attach this capacity and flow to this object. So it's usually not a problem. Now, yes, so I understood it for simplicity. So for simplicity, it's easier to have these indices here, yeah, because it's more visual. If I say E here and say that the edge E connects V and U, it will make everything more complicated. Now, yes, I didn't write that FUV is non-negative because it may be negative. Yeah, for this reverse edge, the flow will be negative usually. Yeah, but for this forward edge, the flow will be non-negative. No, why it will be non-negative? No, because for this residual edge, we'll have the flow is equal to minus F VU. Yeah, and it should not be more than the capacity of this edge. Capacity is 0. Yeah? So minus flow for this edge is not less than 0, no, not greater than 0. And now you just invert this in equation, and you have that flow over the edge VU is greater or equal to 0. Yeah. So you don't need this equation actually. Now what about balance? What about balance? So this balance equation will be simplified because again, when you just take sum of all edges going out of your node, you will have these edges with plus and these edges with minus. Yeah. So the balance equation is very simple. So we have sum for all VFU for all U is 0. And this equation is more simple. So in this equation again, if you just summarize everything going out of the node S, you will have this sum with plus and this sum with minus. So F is just sum of everything going out of the S. Yeah. Mm-hmm. Nice. Now let's prove some important theorems. Will be very few theorems, but it's kind of important. First important theorem. Let's talk about sum of the flows. So, if you have sum of two flows, what does it mean? It means you have just a flow, and the flow over each edge is equal to sum of flows in these two different flows. It makes sense. So, if you take flow for each edge equal to f, let's say 1 UV plus f2 UV. And the important theorem is that every flow can be decomposed into set of paths and cycles. So every path, every flow may be decomposed as sum of f1 plus f2 plus and so on fk, such that if each of them is a path from S to T or cycle. Cycle. Let's prove it. What does it mean, path or cycle? The flow is the path. I mean that you have some path, yeah, from S to T. And you have flow only on these edges. So you have this. No, you have the same flow, obviously, for all these edges, and for all other edges is 0. Yeah. And no cycle is in the same way. So if you have a cycle, you may have some same flow flowing around the cycle, and everything else is 0. Yeah. So we can decompose the flow into smaller flows like this or like this. Let's prove it. We'll prove it constructively. So we'll just construct this set of paths and cycles. How we do it? We take the graph and try to find some path which can we subtract from the graph from the flow. How we do it? Let's find any path from S to T such that flow for each edge is non-negative. How we do it? So we start from the source. We take the source. Now we take any edge with positive flow. Yeah. For example, let's take this edge. So we take this edge. Now, if you go to some node and you have ingoing edge with positive flow, then there must be another edge with positive flow going out of this node because the balance is 0, right? So if you have ingoing edge with positive flow, you must have outgoing edge with positive flow. So let's take any outgoing edge with positive flow. For example, this edge. That's only one. Yeah. Now you reach vertex T. If you reach vertex T, it means you found the path from S to T such that all flows on the edges of this path are non-negative. Now what we can do? We can take this path, take the minimum of the flows over these edges and subtract it from the whole path. So we see we have 3 units here, 8 units here. So the minimum is 3. So let's just say that the first flow is like this. So we have 3 units here and 3 units here. And now we just subtract this flow from our flow. So we will have 0 here and 5 here. Now do it again. Again, you start from the source node, take any positive flow from the source node and continue until you've reached the node T. So start from here, take this node, edge, take this edge. The minimum is 5, so the second flow F2 will be like this. Now again, you just subtract it flow. So we have 5 here and 0 here. And finally you do it again. Now again you start from the source node, take any positive edge here, any positive edge B, any positive edge G. So find this. So find this path, and again your third flow will look like this. Say 5, 5, and 5. That's all. We just decomposed the flow into 3 simple flows. Yeah. So each of these 3 flows is just simple path from S to T. You may also have cycles. Well, this graph is a cyclic, so it's hard to build cycle in this graph. Yeah. But if your graph contains some cycles, then you may have some cycles in your decomposition. How to find cycles? So in the same way, you take any positive edge. Yeah. So if you want to find cycle, you take any positive edge and just start from this point. Again, you start from this point, you find any positive edge, any positive edge, any positive edge, and so on until you reach the cycle. Again, if you have ingoing positive edge, you must have outgoing positive edge. So you cannot stop. You will stop only if you find a cycle. Okay. Oh, that's working. Something wrong with my cable. Okay, the cable is bad. Okay, try not to touch. This cable just not working. Okay, I'll try not to touch it again. Okay. Once again. So why this process even stops? So again, what is the process of finding this sequence of flows? I find any path from S to T with positive flow on each edge. Take the minimum of these flows and then subtract it. Or I can find a cycle. If I find a cycle, I take minimum of all flows around the cycle and again subtract it from everything. Why this process is finite? Why it even no, actually I want to calculate the total number of all flows in this decomposition, but why is it even finite? Why this process will stop at some point? Any ideas? We decrease the sum of the flows. That's true, yes. In this process, we decrease the sum of the flows, yes. So on after each iteration, the total amount of flow along all edges is decreased. But it's that's correct observation. But it will not happen. So if you have big numbers in each, if you have integer numbers, it will end at some point, right? If you have some real numbers, then if you decrease some real function, it may not reach the zero. Okay? There is even much more powerful observation. of the flow, is capital flow, is the value flow. Yes, this is the value of the flow again. What's happening is each time we find the path or find the cycle, one of the edges became 0, right? Yeah. So when we find a path, we find the minimum and then subtract this minimum from everything. One of the edges became 0. It happened on each stage. So each time we find one of this path or one of these cycles, one of the edge became 0. And we have at most m edges. So the number of path of these paths and cycles in this decomposition cannot be more than m. No, here I use f for a value of the flow, and here I use f as flow. Yeah. Yeah. You can write it like this, but it's, yeah. I think it's overcomplication. Usually it's clear enough when I use a value of the flow. When I use flow, it's okay. Maybe not as clear, but. Now here I say that flow f is sum of two different flows, yeah, like this. Okay. Now, I need to erase something. Now, another important thing about flows is what is called residual capacity. So we have some flow. You have some flow. Let's have not maximal flow. Let's have some flow. What do we have? 5 here. Let's have something like. Let's go with 9 here and 5 here and let's put 6 here and 3 here, for example. Strange flow, but okay, let's do it. Now we have 6 here, let's put 2 here and 8 here. Something like that. So let's have some flow. What I want to do is to build what's called residual network. What does it mean? I will, for each edge, I will calculate how much more flow I can push through this edge. It's called residual capacity. What is it? It's just difference between the maximal possible flow and the current flow. And I will build the following network. I will build a network which contains all the same edges with these capacities. So I will build a network with all its residual capacities, and I will remove all 0 edges because I don't need 0 edges. So I will build a network with the same set of nodes, same set of edges, with these capacities, and I will remove all the 0 edges. So I will remain only edges with residual capacity greater than 0 will remain. So let's try to build it for this graph. For example, again, we have some graph, we have some network. It's called network in this theory. So we have some network, we have some flow. Let's build the residual network of this flow. How is done? You build the same network. So you have the same 4 nodes. Now you take the edge, for example, this edge. For this edge, current flow is 9, the maximum flow is 10. So the residual capacity is 1. Yeah? So you just make one edge with capacity 1. Again, this 1 is difference between the maximum flow and current flow. And do it for all other edge. For this edge, the difference is 2. For this edge, the difference is 0, so we don't make this edge. Yeah. The edge with residual capacity is 0 is called saturated edge. It's not a big thing, but just if you see the term saturated edge, it means that the current flow equals to the maximal capacity. Now, for this edge, residual capacity is 3. For this edge, residual capacity is 0 again. But that's not all. That's not all. We also need to add the reversed edge we added before, right? So for each edge, we have also the reversed edge, and we'll add them to the residual network as well. For example, for this edge, so we have this reversed edge. Yeah? The flow for this edge is -9, and the capacity is 0. So the residual capacity will be 0 minus -9, right? So the residual capacity is 9. And we do it for all edges. For this edge, we have the reversed edge with the residual capacity 3. For this edge, we have edge with residual capacity 2. For this edge, we have the reversed edge with residual capacity 6. And here we have edge with residual capacity 8. Now that's all. Now to the algorithm. Okay, let's go to the algorithm. The algorithm will be very simple, a very simple algorithm. Algorithm will look like this. It's basically the same as we did with the bipartite matchings. So we'll start from the empty flow. Empty flow is correct flow. Yeah. If every flow for each edge equal to 0, then all the constraints hold. Yeah. So we have balance equal to 0 because it's sum of all zeros, and the flow is less or equal than capacity. Capacity is always non-negative. So if you just start with all, if you equal to 0, so that's the algorithm from this point. Yeah? So we start from the flow with all flows equal to 0. So very simple flow. It's flow with value 0, but it's a correct flow. And now we'll try to increase this flow. How will we increase the flow? We will increase the flow by finding a augmenting path. Our augmenting path is just a path with residual capacity greater than 0. So we'll find augmenting path. It's the following thing. So we'll find some path from S to T such that for all these edges, the residual capacity is greater than 0. Now, if we find this path, what can we do? No. What does it mean if residual capacity is greater than 0? It means that our current flow is less than maximal flow. Yeah. So it's residual capacity is kind of a value, a maximal value. We can increase the flow for this edge. So we can increase the flow over all these edges. So how can we increase the total flow? We'll just take the minimum of all capacities. So let's say the delta is the minimum on path. Yeah. So we find the flow with all residual capacity greater than 0, then take the minimal residual capacity on this path and just increase all the flow of this section. We have plus delta for all these edges. Now it's easy to see that if you take the minimum of all these C primes, then you will have the constraint, right? So if you increase the value of the flow by this delta, then after this the flow will still be less or equal than the total capacity. Yeah, that's basically the whole algorithm. This whole Ford-Fulkerson scheme. So this Ford-Fulkerson algorithm, very simple algorithm. We start from zero flow. Now each time we build this residual network, now we're trying to find the path in this residual network. So again, this path, augmenting path, is just any path in the residual network, because we removed all the edges with zero residual capacity. So if we just find any path in the residual network, we will find some augmenting path. So we take this residual network, find any path from S to T. For example, let's find this path. So we find this path. Calculate the minimal residual capacity on this path. It will be 1. So delta is 1. And now we just increase the flow for these edges by 1. So we'll say this flow is now 10. This flow is now 4. Now we rebuild the residual network again. No, I will not rebuild it from scratch. I will just update it, right? So I will update my residual network. Here I will have 0. Here I will have 10. Here I will have 1. And here 4. Now we do it again. Again, we find the augmenting path. Augmenting path is any path in residual network. So we find any path in this network. We will have this path. So we go here, here, and here. Find the minimal value among this path. So again, delta will be 1. And now we apply this augmenting path to our flow. What does it mean? We just increase the flow for all edges by 1. So for this edge, we increase the value by 1. This would be 3. Now this edge is the reversed edge of this edge. What will happen if we increase the flow on the reversed edge? We will decrease the flow on the main edge by 1, right? So the flow for this edge will be, so what's actually happening? So we have this reversed edge, right, from this loop, and the flow is -6. So we'll increase it, it will become -5. So flow for this edge will actually be 5. And here we have 5. No, that's basically why we need this these additional edges, these reversed edges, because augmenting paths in your main network look kind of like this. So this is the augmenting path in your network. It doesn't look like a normal path. So what does it mean? What we just did? We increased the flow here, decreased it here, and increased it here. So this augmenting path, if we put it here, it will, for some edges, it will go in normal direction. For some edges, it will go in opposite direction. And what does it mean? If you go in normal direction, you increase the flow. If you go in the opposite direction, you decrease the flow. But since we have this symmetrical form, all these things are the same in this residual network. So this edge means we need to increase, this edge we need to decrease, and we do it in the same way. Very useful. Cool. That's all. That's the whole algorithm. Let's write the code. The code will be actually very simple. The code is very simple. Again, you need to do this you need to do kind of 3 steps. Yes, you need to find the path, then calculate the minimum, and then increase the flow by this minimum. Why does this work? It's a very good question. I hope you didn't ask, but yeah. Yeah, that's a really good question. I didn't answer. Yeah, right. I plan to do it. Yeah, I'll just put it here for future. So, what happened if we didn't find any augmenting path? Actually, it means that the flow is maximal possible. So I claim that if I don't have any path from S to T in the residual network, then there is the current flow is maximal possible. Yeah, that's the idea. I will prove it later. Let's just put it here. Yeah, I will prove it a little bit later. It's just easy to prove it when we talk about cuts. Yeah. Now, next, code. Yeah, let's just code it. So I need to do 3 steps. I need to find path, find minimum, and then increase by this minimum. I will do it all in the same DFS. So I will write DFS. And the DFS will do all 3 things. So how to write DFS? We do 3 things. Like the same way we did it when we talk about bipartite matchings. So in bipartite matchings, we need to find the path and then reverse the path. Okay, invert the path, right? So, and we find the path in the DFS, and when we go back and from the recursion, we inverse the path. Here we'll do the same. We will do a DFS. So how DFS will work? So you start from the S, yeah? Now you have some node V. So this is the current state of your DFS. What you need to do is to calculate minimum on this path. So I will calculate this minimum. Let's consider min. Yeah. Now, so when I reach vertex T, I will find the minimum on this path. Now, when I go back from the recursion, I will apply this delta to the to the level. So then I will go back from the recursion, so I find this T, and then I go back, I will apply plus equal. Yeah. I will apply this increment to the tail of my path. So I go back from the recursion and apply this increment to this path. Yeah, that's the plan. So my DFS calculates minimum when it goes this way, and then goes backwards, it applies the increment. Let's see. So I have 2 values. I have F and minimum. Oh, no, I don't like this M. Let's call it small delta. Okay. So this small delta is the minimum on this suffix or prefix. Well, let's see. So how to write DFS? You know how to write DFS, right? So we see if it is marked, we return 0. So the function DFS will return the amount of flow it can push. Yeah. So it will return this delta. So now the mark node. So this is just simple DFS. Now we iterate for all 8. So now if node is T, it means we reach the vertex T. So we just return this current minimum. So again, we return the minimum we found during this DFS. Yeah. If we reach the node T, it means we found the whole path. So this delta is the current minimum. Yeah. Now we just iterate for all edges. Edges VU, which has positive VU. So we iterate for all edges with positive residual capacity. No, you can iterate over all edges and then just check if the residual capacity is positive. Yeah. Just erase it. Okay, let's do it in 2 steps. I have enough space here. So if the let's rewrite it. So residual capacity is just C minus F. So if C minus F U V is equal to 0, then continue. Yeah. Like this. So now I have edge from V to U with positive residual capacity. Let's call DFS from this node. So let's say delta equal to DFS from this U, and I need to update my minimum. So my minimum will be minimum of this minimum and the residual capacity of this node. Like this. That's so. Now if I find something, so if this delta is greater than 0, it means I reach the node T. Yeah? If I reach node T, then I already updated this part of the path, and I need to update the next edge. So I need to update this edge VU. Update this means increase the flow by this delta. So I increase the flow VU by delta, and I decrease the reverse edge. And return. If I didn't find anything, I just return 0. That's all. And now you just call this DFS until you have no path. So again, if there is a path in residual network from S to T, this DFS will find this path, right? So if this DFS returns non-zero, it means it found some path from S to T and updated the flow along this path. If this DFS returns 0, it means there is no path from S to T. If there is no path from S to T in the residual network, it means our current flow is maximum. We will prove it later. Okay. Very simple. So the algorithm is very simple. You just call this DFS until it returns 0. When it returns 0, your flow is maximal possible. Okay, now let's stop here for a second and talk about time complexity. Let's talk about time. What is time complexity of this algorithm? No, time complexity of DFS is obviously linear, right? So time complexity of this DFS is m. Yeah, so it's the size of the graph. How many times can we call this DFS until the flow is maximal possible? What do you think? So, if we just run this DFS over and over again until it returns 0, what is the maximal number of times can we do it? Yeah, it looks like in the previous part we just proved we can decompose any flow into no more than f paths, m paths. So it looks kind of the same. We kind of find paths and then form the big flow from these paths. But unfortunately, life is. The reverse edge starts with maximum flow. No, we start from the 0 flow for all edges, for both main edges and reverse edges. Okay. So the life is a little bit more complicated, unfortunately. So let's look at the following graph. If you have a graph like this, let's have 100 here, 100 here, and here, and here, and 1 here. What might happen? Don't DFS find any path, right? So if it is not smart enough, you can find this path, for example. So this is a nice augmenting path. Yeah? This is a nice augmenting path. You can increase the flow using this augmenting path. So you have one here, and one here. What will happen in the residual network? In the residual network, we have something like this. So you have 99 here, one back, 100 here, 100 here, 99 here, one back, and here this edge is saturated, so it will be removed from the residual network. But the backward edge will happen in the residual. So you will remove this edge from the residual network and add reverse edge to this one. So you have backward edge with 1. Now again, in this residual network, you find the next path. Yeah. So you find any path from S to T, and if you are not lucky enough, you may find this path. So you may find this path. When you find this path, again, the minimum is 1, so you'll increase flow by 1. So you end up with flow like this. So here, 0, 1, like this. And then you do it once again. You find this path, then you find this path, then you find this path, then find this path. Each time you increase the flow by 1. So it may happen that the number of times you need to call this DFS actually is big enough. So here I have 100, but you may have billion here. Yeah. No. Let's just say that each time we increase the flow, so if the flow is bounded by some constant, so each time we increase the flow, right? So the number of times we need to call this DFS is no more than the value of the flow. Yeah. And then each time we call DFS. So let's take complexity. What's the problem here? Problem here is not polynomial, right? We talked in previous semester, maybe in the second semester, but about polynomial algorithms. Polynomial algorithm should be, time complexity must be a polynomial of the size of the input. F is not the size of the input. F is a value of the flow, so it's just a value of these numbers. You can write very big numbers, so it's not the size of the input. So ideally, we want to have this time complexity not depend on this size of the flow. We will do it later, but sometimes it's good enough. Sometimes you know that your flow is small. For example, if you need problems like you have 2 nodes and you need to find 2 paths from one node to another and not intersecting paths. Yeah. So if you have non-intersecting path, if you want to find 2 non-intersecting paths, you can just find flow of size 2 and then decompose this flow of size 2 into 2 paths. So if you know that the size of your flow is 2, then it's fine. Yeah. So if you know your flow is small, that's good enough. If you don't know it, then there may be some problems. Okay, let's go next. Okay, I will leave this here because I want to prove it. To prove it, I will move to another problem. I will move to a problem of finding a minimal cut. Draw another graph. Let's draw another graph. I know it's the same, but let's put something here. Let's say 10 and 3 and 5 and 4 and 8, something like that. Yeah. No? 10 and 3 and 5 and 4 and 8. 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 BFS, we'll move to BFS. Let's wait for it. We'll talk about it. So we'll talk about how to improve this time complexity a few moments later. Let's talk about minimal cut problem first. So what is the minimal cut problem? You have some graph, again, you have some network. You have two nodes, S and T. What is the problem? So these numbers are the costs of these edges. And the problem is to remove some edges such that there will be no path from S to T. And just so there is no path from S to T, like this. This is S. So for example, you can remove these two edges, or you can move these two edges, or you can remove all of them. Yeah. So you remove some subset of edges to prevent anything going from S to T. And these numbers are the costs of the edges. So the value of the cut is just the sum of the costs of all removed edges. Yeah. Let's put UV here. For example, in this graph, what we can do? For example, in this graph, we can remove these three edges, this edge, this edge, and this edge. So total cost will be 9. Oh, 9, right? Yeah. So it's 5 plus 1 is 9. Now, good. So minimal cut problem looks very different from maximal flow problem, right? Now, your problem is to find the minimal cut. Yeah. It looks very different from maximal flow problem, but it turns out that it is actually the same problem. It's dual problem of the maximal flow problem. In the same way that again, when we talk about bipartite matchings, we talk about the bipartite matchings and the vertex cover are the pair of dual problems, right? So if you maximize this, you will minimize that. Here happens all the same thing. So, and again, when we'll talk about linear programming, we will see that actually these are two dual linear problems, right? Let's see. Well, let's prove it. We'll just prove it. We'll just prove it right here. Again, if you remember what happened in the maximal bipartite matchings and minimal vertex cover, what happened is these two problems kind of restrict each other from. So there was two problems. One is trying to maximize something, another is trying to minimize something, and they meet at the same point. The same thing will happen here. So if you look at any cut, so let's take some cut. What does mean cut? So you have vertex S. You removed some edges from your graph. Let's mark everything which is reachable from node S. So we removed some edges. Now node T is not reachable from S. So let's mark everything which is reachable from S. So these nodes are reachable from S. And these nodes are not reachable from S. And T is here. Now, if you look at all edges between these two parts, all these edges must belong to your cut, right? So this is your cut. Now let's think about some flow. If you have some flow in this network, so if you have a flow from S to T, And these costs are actually the capacities of the edges. What you can say about the value of this flow? So the value of this cut will be sum of all CUV for all edges from here to here, right? What we can say about maximal flow? So if we say that this CUV is actually the capacity, yeah, and look at this as a network flow problem, what we can say about the value of the maximal flow from S to T? It's quite simple. So if you have this, you have this flow. It must flow from here to here, right? So there are only these edges going from this set to this set. So the maximum, so the flow is the sum of all flows of these edges is no more than sum of all capacities of these edges, which is C. So if you take any cut and any flow, you can say that the value of the flow is no greater than the value of this cut. So again, we have the same situation as before. So we have some flows here and some cuts here. And all the flows are no greater than all the cuts. And the interesting thing for dual problem is that they actually meet at the same point. So there is this point. So if we find this point, so if we find some flow and some cut with the same value, we will immediately prove that this maximal possible flow and minimal possible cut. It's actually quite common for linear programming problems to prove it like this. So in many linear programming problems, the algorithms look like this. So it kind of builds normal solution and dual solution. And at some point they met, and it means you have optimal solution for both problems. Just okay. So how we'll do it? We will do it in the following way. Again, it is basically the same as we did in the first lecture when we tried to build a vertex cover. We will run the maximal flow algorithm. So let's first. We've built the maximal flow. Yeah. And now we will run the same DFS again. I just raised this DFS, but you run the same DFS again. And mark everything reachable from S in this DFS. No, that's okay. Let's run DFS for all edges with positive capacities. Again, the same DFS. It will mark something. So you have this node S, and you have this node T here. So these nodes are reachable from S. And these nodes are not reachable from S. Now let's look at all edges from here to here. So we have edges from here to here. What can we tell about these edges? Why are these edges not in the residual network? So we run DFS from this node S for all edges with positive residual capacity. Yeah. So we take all the nodes with positive residual capacity, run DFS. These nodes are reachable, these nodes are not reachable. So if we have this edge in our graph, why is this edge, if we didn't go from here to here, it means this edge is actually not in the residual network. Yeah? If this edge is not in the residual network, it means that the residual capacity of all these nodes, of all these edges, is 0. Yeah? So for all these edges, residual capacity must be 0. Right? Because if it is greater than 0, then we will use this edge to go from here to here. What does mean residual capacity is 0? Residual capacity 0 means the edge is saturated. Yeah. So the flow for this edge is the same as the capacity of this edge. So for all these edges, the flow equals the capacity. So they have the maximal possible flow for this edge. Now we just take the sum of this. So the sum of all F's will be the same as sum of all C's. This is the value of the flow, this is the value of the cut, that's all. Okay, so we just did two things. First, we learned how to solve the minimal cut problem using Maxwell flow problem. Yeah? And second, we just proved this thing. We just proved that if there is no augmenting path, then the flow is maximal possible. Again, why it is so? Because if there is no augmenting path, we can mark all the reachable nodes, all non-reachable nodes, take all these edges and find the cut with the same value as the flow. If we find the cut with the same value of the flow, it immediately proves that your current flow is maximal possible. Okay, that's one of the easiest way to prove it. Do we have time? Yeah. Nice. Now I want to talk about two improvements for my algorithm. Maybe two, maybe one, at least one. So we have the algorithm for finding the maximal flow algorithm, or maximal flow in the network. And the time complexity is F by M. Yeah. Now, again, this algorithm is not polynomial. It's bad. Yeah. So we want to improve this algorithm to make the time complexity polynomial. And the first idea is very simple. We will just replace DFS with BFS. It's called the Edmonds-Karp algorithm. It's the same Edmonds who found the algorithm for all this Blossom algorithm, yeah, from the previous lecture. So it's Edmonds-Karp algorithm. It's very simple. We do all the same do all the same thing, but we didn't find any path from S to T. So when we try to find augmenting path, we always find augmenting path of the minimal length. That's all. And now I claim that if on each step we find not any path, but we try to shortest possible path, then time complexity will be polynomial. Again, if you think about the problem we discussed, if you think about the problem we have in this graph, right? For example, in this graph, we have problem because we always find these paths, yeah. And if we replace DFS with BFS, we will not do it, yeah, because these paths are not shortest one. We will find these two paths and just in two steps we will find the maximal flow. Yeah, so it kind of makes sense. Okay, well, let's prove it. So again, I want to prove that if I replace DFS with BFS, and on each step of my algorithm I will try to find the shortest possible augmenting path, then time complexity will be polynomial of the size of the graph. Let's prove it. How to prove it? Let's see. Let's look at the following values. Let's say d of v is the distance from S to V in residual network. So we take the residual network, we take all the edges with positive residual capacity and try to find the shortest path in this residual network. So let's say that d of v is the distance in the residual network. It may change during the algorithm because the residual network is changing. Yeah. When we apply something to the graph, flow is changing, so some edges may become zeros, and they are removed from the residual network. And some edges may become not zeros, and they will be inserted in the residual network. So residual network is changing, so these distances will be changing. So it's not fixed values. They are values for the current residual network. Yeah. Now what I want to prove is these distances are not decreasing. Cannot decrease. Cannot decrease. No, why is it true? No, because of the way how we apply the changes to our residual network. So what we do in our residual network, we always apply change only to this augmenting path, and we try to find augmenting path of the minimal length. So we take this shortest possible augmenting path. So this is the shortest augmenting path. What are the distances for these nodes? So if we look at values d for all these nodes, so d of s is obviously 0. Yeah. So for this node, the distance will be always 1, right? For this node is be 2, for this node 3, and so on. Let's see 4. No, edges are not weighted. Yes, so it's d minimal length just in the number of edges, like BFS. Yeah. No, there are no costs. So we just take the path of minimal number of edges. Now, again, if you look at the shortest path, in any shortest path, distances look like this. So distances is increasing by 1 in any shortest path. Yeah, because you have if this value is 4, it means the distance to this node is 4. Yeah, if you take the shortest path, then you must go from some node with distance 3. Now, again, this part of the path is shortest possible because this path is shortest possible. So if this distance is 3, this distance must be 2, and so on. So if you take any shortest path in a graph, the distances will be increasing by 1. Yeah? That's how shortest path works. Now, what happens? We apply this augmenting path to our flow. So we increase the flow over these edges. What will happen to our residual network? Which edges will be removed from residual network and which edges will be added to residual network? So what changes will be made to our residual network? So again, if you find this augmenting path, again you find the minimal residual capacity on this path, then you increase the path by this delta, right? Like before. So after these changes, your residual network will change. So some edges will be removed, some edges will be added. So which edges will be removed? What do you think? Yeah, we'll remove at least one edge along this path. Yeah. No, the truth is we will the only edges the edge will be removed if the residual capacity was greater than 0 and became 0. Yeah, so the edge became saturated and it is removed. Yeah, so it may only happen when we increase the flow. We increase the flow for these edges. So the only edges which are removed are the edges on this path. And yes, we will always remove at least one edge because we will take the minimum. For this minimum, the flow will become the same as capacity, so if at least one edge will become saturated and will be removed from the residual network. Right. Whew. Yes, and we will add some reversed edges. So some of these reversed edges will be added to residual network. No, because if this residual capacity was 0, when we increase the flow, we will decrease flow on the reversed edge. So for this reversed edge, residual capacity will become positive. Right? Right. So we remove some of these edges and add some of these edges. Maybe not one, maybe many of them. Actually, we'll add all of them. So all the reverse edge will be positive after we play. Now, I claim if we made these changes, distances may not decrease. No, why? Well, first, let's add these new edges. So when we add edge like this, distance to any node cannot decrease. Why is it so? Some node here. Can we use this edge to make better path to this node V? So for this node V, we have some current distance, right? So if we add edges from this node to this node, can this distance decrease? It actually cannot, because if we use this edge, it means we spend at least 2 edges to go here, then we use this, so we spend at least 3 edges to go to this node. But the distance to this node is 1. So this path is always shortest to this path. So this edge will never be in any shortest path. So basically, any edge which goes from the farthest node to the closest node cannot be used in the shortest paths. In shortest paths, you only use edges which goes from closest nodes to the farthest nodes. Obviously. So when you add these reversed edges, you can decrease distance to any node. So distance don't decrease. And now when you erase some of these nodes, distance also cannot be decreased, right? Because when you remove edges from your graph, you cannot find the shortest path, right? So you add these edges, distance is not decreasing. Now you remove these edges, distance is not decreasing. So distance is never decreasing. Okay, we just proved this. So we just proved that this value d is never decreasing. And now let's do the following. Now let's take some edge and follow whole lifetime of this edge. So what happened to some edge? So we have some edge from V to U. So at some point this edge will be removed from the residual network. When this edge will be removed from the residual network, then there is a path from S to T for this edge. So at some point we find path like this. So this edge is the minimum on this path. So it will be removed. So this is how we remove edges from the residual network. So each time we remove at least one edge. Yeah. So for any edge, there may be some point when we find some path and this edge is minimal possible. So we remove this path, this edge. We remove this edge. How can we remove it again? So before we try to remove it again, we need to add it back. Yeah. So I want to calculate number of times we can remove the edge. That's what I'm trying to do. So if you take some edge, let's calculate how many times can we remove this edge from the residual network. So we removed it the first time. Before we remove it the second time, we need to insert it back. To insert it back, we need to, again, we insert edges like this. So this edge must be a backward edge. Yeah? So we must find a path like this. path like this. So we update our flow using this augmenting path. And when we find this augmenting path, we will move this edge back here, and so on. So this is how the life of the edge looks like. Yeah. So we have this edge. At some point, we find some augmenting path. This edge is minimal possible, so it is removed from the residual network. Then we will find path like this, and we put it back to the residual network. And when we find path like this, and we remove it again. Now I want to claim that it can't be happened too many times. Why is it so? No, let's see. First time, when we remove this edge from the residual network, this path was short as possible. So when we remove this edge, distance to u was equal to distance to v plus 1, right? It's when we remove this edge. Now, when we put it back, we use this path. So next time when we put it back, new distance to node v must be new distance of node u plus 1. Yeah? So here we remove, here we insert. Now, the distances are not decreasing, so new distance of node u is greater or equal than all distance of node u, right? Now I'll just apply it here. So this new distance to the node v is greater or equal than distance node u plus 1. Distance to node u is distance to v plus 1. So it's greater or equal than distance to node v plus 2. What does it mean? What does it mean? It means if we look at some edge, and again, we look what happens to this edge. At some point we remove the edge, then put it back, remove and then put it back. Every such cycle increases the distance node v at least by 2. So if we remove the edge and then insert it back, the distance to node v must be increased by at least by 2. Clear enough. So distances are bounded. So all the distances cannot be more than n. No, n minus 1 doesn't matter. Okay. So we cannot increase distances more than n times. So this loop can't happen more than n times. That's all. Now just see. So for each edge, we can remove the edge from the residual network at most n times. We have m edges, so the total numbers of removals of all edges from our residual network is at most nm. So at most nm times, we remove edge from residual network. But we remove at least one edge for each augmenting path. So we find augmenting path, we remove at least one edge from the residual network. We can't remove the edge more than nm times. So the total number of times total number of augmenting paths can't be more than nm. So we call DFS nm times. Each DFS goes to m time. So the total time complexity will be nm multiplied by DFS. Yeah, so it will be nm squared. Good. Yes, it looks scary. It looks scary. It is. Again. It is worse time complexity. So you can build a graph with which kind of satisfies also. You can build the worst case for this algorithm. It's not that hard, but usually for some typical cases, time complexity won't be that bad. Again, if you know your flow is small, like here, time complexity again. Each time you increase the flow, this time complexity also satisfied. Yeah. So this is just the worst case time complexity. Again, usually you may think about again. Usually what happened, you don't have just some, you're not given some graph from outside and just run the network flow problem. You don't try to find maximal flow in some arbitrary graph given you by something. So usually you have some problem, and from this problem you build your graph. So it's not just some arbitrary graph, it's some specific graph. So for some specific graph, time complexity may be much better. So usually if you have some specific graph, there's something interesting about the graph which makes the algorithms of finding maximal flows work faster. We will discuss faster algorithms in the next lecture. That's we'll talk about scaling or next time. How do you prove the first theorem? What composition? Yes, we didn't use it. Yeah, it's just interesting theorem. It's just useful. It's just useful to think about flow as the composition of some paths. Yeah. Yes, but we didn't use it, right? Okay, let's talk about scaling. To save some time in the next lecture. So, another cool technique about graphs is the scaling. There are different techniques called scaling. They all do basically the same thing. What was the problem in the first algorithm, in this algorithm? Why can it work slowly? No, because we find bad augmenting paths. So we find augmenting paths, minimum is small, so we increase the flow by the small amount. Let's try to find good augmenting paths. So let's try to find augmenting paths with minimal residual capacity at least 2 in the power of k. It's n. And then we'll decrease the value of k. So first we'll set a big value of k. So we'll say, so k will be decreasing from log c to 0. So first we'll set a big value of k and try to find very good paths which increase the flow by big amount. And then when we don't find any paths which increase the flow by 2 power of k, we will decrease k by 1 and find some smaller paths, and so on. In the end, k will become 0, so we will find any path with at least 1. Yeah, it works only for integers, but you can do it for real numbers as well, but yeah, you will have some details. Okay. Very simple algorithm, right? Again, you can find augmenting path with all capacities at least 2 in power k using the same DFS. You just change this how it's called condition in your for loop just to check. You iterate all edges and just check if the residual capacity is at least 2 in the power of k. we checked that the residual capacity is positive, but you just change it to check if the residual capacity is at least 2 in power of k. What will be time complexity? Let's go. Now, let's see. Let's see what happened in each iteration. So we have iteration k. Yeah. So we're trying to find paths of value at least 2 in power of k. Why are we doing it? Because in the previous iteration we didn't find anything. So let's have iteration k. It means we have no path with at least 2 in power of k plus 1. Yeah. Yeah. So if we have iteration k, it means we finished the previous iteration. In previous iteration, we're trying to find paths of capacity at least 2 in power k plus 1. So we didn't find anything, so we go to iteration k. So what does it mean? If we don't have any path with capacity 2 in power k plus 1, it means again we have some cut. Yeah. So again, we run this DFS. So these nodes are reachable, these nodes are not reachable. And for all edges in this cut, we have the residual capacity less than 2 in the power of k plus 1. Yeah. So again, if in the previous iteration we didn't find any augmenting path with capacity at least 2 in the power of k plus 1, it means we have some cut. Yeah. So these nodes are reachable, these nodes are not reachable. All nodes in between, all edges in between must have capacity less than 2 in the power of k plus 1. What does it mean? It means we can't increase our flow too much. So the difference between maximal flow and our flow can't be more than the value of this cut. And the value of this cut is no more than 2 in the power of k plus 1 multiplied by the number of edges here. So it's m. So we have some edges from here to here. We cannot increase the flow more than the total capacity of all these edges. Total capacity of all these edges is no more than 2 in the power k plus 1 multiplied by m. Right? But here, each time in iteration, we increase the flow by the value 2 in the power of k. Yeah. So in iteration k, each time we find a new path and increase flow by value 2 in the power of k. But if this difference is no more than 2 in the power of k plus 1 by m, we cannot do it more than 2n times. Right? Again, this is different between maximal flow and our current flow. It is no more than the total capacity of all these edges. If each time we increase the flow by 2 in the power of k, we can increase it more than this difference. So we just divide this by this and to get to m. So on each iteration, we do no more than 2m. We find no more than 2m augmenting paths. So the total time complexity will look like this. So we have log c iterations. On each iteration, we find augmenting paths. We find no more than 2m augmenting paths, and each augmenting path we find using DFS, so it costs m times. So it will be log c multiplied by m squared. Like this. So what is better, nm squared or log c m squared? Good question. Depends again. Again, this is strongly polynomial algorithm. It depends only on the size of the graph. This is also weak polynomial algorithm. Weak, right? So this is weak polynomial algorithm. So you have this log c in your polynomial. It's usually good enough. So log c is basically the size of this number. Yeah? So it's like the number of digits you need to use to write this number. So it's kind of polynomial, but not strongly polynomial like this. Both algorithms are useful, and actually we will combine all these techniques in the next lecture to build even faster algorithm. Okay, some spoilers for the next lecture. What we will do, what people can do. There is an algorithm which works in time complexity NM, but it is very complicated. We will not talk about it. But people, that's one of the best algorithms people know. People know slightly better algorithm for some cases, but we will go pretty close to this time complexity. We will discuss algorithm which works in NM log n. So this algorithm we'll discuss in the next lecture, maybe in 2 lectures. So at some point we'll discuss this algorithm. And we will discuss algorithm with this time complexity. So I plan to discuss these 2 algorithms, and it's pretty close to the best known algorithm for the Maxwell flow problem. So by this log factor, yeah. So it's a plan for the next lectures. Okay, I think that's all for today. See you next week.